Everyone, we're starting chapter 11 here, which is this idea of gravitation. And I do have to say this is probably one of my favorite chapters of mechanics. So what we're talking about here is we're talking about why things have gravity and what gravity does to objects. So this is a very early idea of how the solar system looked. Each sphere there, the one in the middle, is the sun, and then each little dot is one of the planets. You can see Earth on its tilt with our own little moon going around us, and so on and so forth with Jupiter and Saturn and all the other, at least the planets that are visible to us on this diagram. So we go to the myth of Newton's apple, and everyone knows that an apple fell on Newton as it hit the ground, and when it hit him in the head, he said, gravity. But the way the legend goes is that when he actually was struck in the head, he looked up and he looked at the moon, because the moon was up during that time of the day. And he said, well, if the apple falls on me due to gravity, why doesn't the moon fall on me? So when Newton looked up and looked at the moon, he saw that the moon traveled in a circular path. So knowing that the moon goes around us every single month, takes around 28.2 days for the moon to make one orbit, 1 month until the moon returns to the same spot in the sky. So due to understanding forces and motion, he thought, well, there must be some force that's forcing it in towards the center of the circle. What's causing that moon to accelerate? And why is it accelerating towards Earth? So in 1686, he came up with his universal law of gravitation, and here is it stated. The universal law of gravitation says that every object in the universe will attract every other object in the universe with a force that's proportional to their masses and inversely proportional to the distance they're separated squared. So the gravitational force equation there is, force of gravity is big G, mass 1, mass 2, multiplied all together, divided by the distance between the two masses squared. And the big G is this gravitational constant of 6.67 to 10 to the minus 11. Units for the gravitation constant there are Newton meters squared per kilogram squared. So what you can see here is that I've got two masses, and those two masses are a distance apart, and you can see that there's a gravitational attraction between them. If I want to increase the gravitational attraction, I can simply increase the object's mass. The more mass the object has, the more the gravitational attraction increases. If I make the other mass increase, now you can see the gravitational attraction is going up even higher. But there's something we can do to increase the force of gravity without even having to touch, and that's simply by grabbing one of the masses and moving them. If I move the mass close to another mass, that decreases the distance between the two of them, and the force of attraction increases. I can simply go the other way and move the masses far apart, and the further apart two masses are, the lower the force. Now if you look at the force of mass 1 by mass 2, we're talking about very, very small units of force. We're talking around 696 nanonewtons of attractive force. So why is that? Let's check out the units and understand why that is. So if I was going to do the gravitational attraction between myself and a 1 kilogram mass, I can put those into my gravitational force equation. So I've got my mass of 68 kilograms, I've got the 1 kilogram mass next to me, and let's put it a meter apart. And don't forget to square that. So multiplying those out, you'll do 68 times 1 and gives you 68 over 1 meter squared gives you 68. And I'm going to take 68 and multiply by 6.67 times 10 to the minus 11. This to the negative 11th shows that the gravitation constant is very, very weak. It's very, very small. And if I look at my units here, I'm going to have meters squared on the bottom and a kilogram times a kilogram on top, which will cross out everything in the gravitational constant unit, leaving me just a Newton behind. The gravitational constant has units that will make us have newtons in the end because we're looking for force. So the attraction between myself and a 1 kilogram mass comes out to 4.5 times 10 to the minus 9th newtons of force, which is around 4.5 nanonewtons of force. So that's the reason when I walk into the classroom and I get close to a 1 kilogram object, that object does not jump off the table and come towards me. It is attracted to me, but it is with such a tiny force that friction can easily overcome our gravitational attraction, and it does not jump off the desk towards me. So if we were trying to determine your force of gravity between yourself and the Earth, we are attracted to Earth. You have mass, the Earth has mass. So let's try and calculate the attraction between yourself and Earth. If I want to find my force of gravity, so I take the gravitational constant g, multiply by my mass, and I multiply by the mass of the Earth, which, if you don't have that memorized off the top of your head, it's 5.98 times 10 to the 26th kilograms. So the Earth is extremely massive. If you want to write that number out, that's 598 followed by kilograms. So that is the mass of the Earth. That's billions upon billions of kilograms compared to my mass. So we've got the two masses that are attracted to each other. We got the gravitational constant, and now what we need is the distance between myself and the Earth. And one thing you're going to be tempted to say is that, well, I'm standing on the Earth, so the distance is my height. How tall am I tells you how much distance there is between myself and the Earth. But I do want to point out that when you do that R measurement, it is the distance from the center of one object to the center of the other object. So the center of you is just really right around your belly button. But for the center of the Earth, you're talking about from the middle out, right to where you're standing. And since your distance above the ground does not even compare to how big the Earth is, you can just use the radius of the Earth for the distance between you and it. So the distance between myself and the center of the Earth is 6.37 million meters, or 6.37 times 10 to the 6 meters. And remember, don't forget to square it. You'll forget to square it. Don't forget to square it. So if I put that in my calculator and I do all the work, what I end up getting is around 667 newtons. That's the gravitational attraction between myself and our planet. Now, if the Earth pulls down on me with 667 newtons, I must pull the Earth back up with an equal and opposite force. So I technically am lifting the entire Earth up on top of me with 667 newtons. But why don't I notice the Earth come up to meet me? Well, the big thing is the mass. Since I have such a small mass, when we talk about equal and opposite forces, both myself and the Earth have the same force on us. However, my mass is very tiny, and the Earth's mass is humongous. That means that when one of us falls, if I fall to the Earth or the Earth falls up to me, we notice my acceleration towards the ground, and we barely notice the Earth's acceleration whatsoever. So really, the effect is the acceleration. The force is the cause, and both of us have the same equal and opposite force. But that's 667. That number just seems to be bugging me. When we used to calculate force of gravity, I used to just take my mass and multiply by g, which was 9.8. Well, in my equation here, I do see mass as 68. So what would be g then? Well, to give myself gravitational acceleration, I take 5.98 times 10 to the 26th, multiplied by 637 to the 6 squared, and multiply by the g constant. And if you take all three of those and multiply them, it'll actually spit out 9.8 meters per second squared. So the g times the mass of a planet divided by the planet's radius will actually give you the gravitational acceleration of that planet. You don't even have to go to that planet, and we can tell you exactly how much you'd weigh knowing the planet's mass and knowing the planet's size. So in order to find the gravitational acceleration, like we do for each planet, you can take the gravitational force divided by the mass of the object you're interested in. And if you look at those two equations, I've got the gravitational force equation as mass 1, mass 2 over distance squared. And I'm going to divide by the mass to find acceleration, and that mass is my mass. So it doesn't matter what mass you drop in a gravitational field, all will accelerate at the same rate on each planet. That's why we can drop heavy things and light things, and they all will accelerate at 9.8. So one thing you might be asked is some questions about like ratios. Like what happens if one mass doubles and the other mass doubles? What does that do to the gravitational strength? Well, what you can do is just simply double the masses and put them back into that giant equation again and see what you get. But since we know we can play with ratios, we can do this ratio very quickly, and I'll tell you right off the bat how much the gravitational force changes. So in the example I just gave you, I said let's double both masses. So I'm going to put a 2 in front of that mass and a 2 in front of that mass. I'm going to keep the distance between them the same, so I'm going to put a 1 there. So what I want to do is I want to pull out all the numbers and leave the equation behind. So on top it's a 2 times 2 or 4, and on the bottom it's a 1 squared or 1. So right off the bat here, if I double both masses, the gravitational force will increase by 4. That's just a simple, easy ratio. Let's try another one. Let's have one mass increase by 3, the other mass will increase by 2, and the distance between those will double. So when we do our work here, let's pull out the top. 3 times 2 is a 6. And on the bottom, our distance is doubled, but don't forget to square it. So 2 squared gives you 4. So it's 6 over 4. The gravitational force is going to increase by 1.5. How about decreasing our gravitational force? Well, I could decrease my masses, but the easiest thing to do is let's simply increase our distance. On the top, it's 1 over 1 times 1, or 1 on top. 3 squared on the bottom is 9. So the force of gravitational attraction decreases by 9. And we can do the same ratios with our gravitational acceleration that we got from before. Just depends on the gravitation constant, the mass of that planet, and the radius squared. So again, we know Earth gravity is around 10 meters per second each second, putting in Earth mass and Earth radius. But let's say our planet got twice as massive. Twice as massive gives us 2 times the gravitational acceleration. So that planet would have 20 meters per second squared be its gravitational acceleration. If I would double the radius at the same time, remember radius is squared on the bottom there, so you'd actually have 2 over 4, or half the original gravitational acceleration. So just making the planet bigger doesn't necessarily give you more gravity. Making it more massive gives you more gravity, but increasing the distance actually decreases the amount of gravitational acceleration. So the G constant, I just kind of threw it out there and gave it to you, but where did it actually come from? Well, it came from a guy named Cavendish. Newton knew that there was some constant for his equation. He had it just really, the force of gravity was mass 1 times mass 2 over distance squared. But he did not know what the G constant was. Once you have the G constant, you can calculate masses for anything that you want in the universe. I mean, we're talking about a universal gravitation law. So the Cavendish experiment, almost 100 years after Newton, is something like this. You have 2 masses, and you put them a certain distance apart. If you click the video below, you can watch that when the 2 masses are next to each other, nothing in between them, just their own gravitational attraction, the 2 masses will pull together and spin this little fiber. That fiber creates a force. Looking at Newton's equation here, we've got the force in the tension. We know mass 1 and mass 2. So we have both of these guys. And you know how far apart those masses are separated, so you know the distance. Knowing those 4 pieces of information allows you to calculate the G constant. So again, check out that video below and make sure you can watch 2 masses attract each other with nothing else besides their own gravity. And since we've been able to play around with ratios, we can also say that any quantity that changes with respect to a 1 over r squared, any value that follows the relationship of 1 over r squared is called an inverse square law. So the example I have for you here is the butter gun. The butter gun explains what happens to gravity just by changing distances. So if you want to think about it, let's say we have a gun that shoots out butter. And at a certain distance, we'll call it D, that butter shoots out and hits the entire piece of toast here. And it covers it with 1 inch of butter. Now that's a lot of butter, and that's pretty thick. So if you want less butter, we need to step backwards. We're going to double our distance. And if we double our distance now, the spray is going to be able to go out and hit more pieces. So you'd think, okay, it can now hit 2 pieces. But you have to think, the spray is not just going out left and right, it's going out up and down as well. So you can also hit 2 pieces up and down, so you end up hitting 4 pieces of toast. But now that that butter has spread out, there's only 1/4 inch of butter on each of the pieces of toast. What happens if we triple the distance? So tripling the distance means I'm going to spread out 3 left and right and 3 up and down. I'm now going to hit 9 full pieces of toast. But now that I can hit 9 full pieces of toast, the thickness of the butter is getting thinner and thinner and thinner. It's actually going down by 1/9. So what you're seeing here is that every time I change the distance, I'm decreasing the quantity by 1/r squared. So if I went 5 times further away, I'd be able to hit 25 pieces of toast, but the thickness would be down by 1/25. Gravity follows the same relationship. When you move twice as far away from the planet, the gravitational attraction between you and that planet goes down by 1/4. You triple your distance, it goes down by 1/9. You 10 times your distance away from the planet, your force of attraction goes down by 100. So it quickly drops off. But that's just going away from something. What if you get closer? What if you cut that distance in half? Well, you're obviously not going to be able to hit the entire piece of bread there. So the butter's going to pile up in one location, and the thickness is going to be really, really thick. How much thicker? Remember that it's 1/distance squared. So I have to take 1/2 and square it, which again gives you 1/1/4. So 1/1/4 means that you're going to get 4 inches of butter right here on one piece. It's not going to cover the entire piece, but that butter is going to be extremely thick. So to increase gravity, come closer. To decrease gravity, start moving further and further from objects. In class, we'll show demonstrations about how things are attracted to each other, how you can calculate them, and why masses even cause things to be gravitationally attracted to each other.